312, Laplace's equation in one dimension. So if we constrain ourselves to only one dimension, Laplace's equation becomes, well, rather trivial. So it becomes d squared by dx squared of the potential equals to 0. Now, if you've taken your basic physics course, you should recognize, that this integral basically says the acceleration is 0, so you have something with like some constant velocity. Okay. So there's a solution for that, the general solution. We have two constants we need to find, m and b. And in order to get two constants for a simple algebraic expression, we need two boundary conditions. So suppose we know that, let's say v of 1 is equal to 4. I'm using the book's example, by the way. And v of 5 is equal to 0. Well, then we find the slope. So m is going to be v of 5 minus v of 1 all over 5 minus 1, which is 0 minus 4 over 4, which is made at minus 1. And then you plug in one value, so you say v of 1 is equal to 4. Well, that's going to be equal to minus 1 times plus b. So it's equal to minus 1 times 1 plus b. So we basically, 4 minus 1 is 3 equals b. So we get the equation v of x. And you're not even seeing this, are you? Sorry about that. V of x is equal to negative 1 x plus 3. So very trivial to solve. And to be honest, you might be wondering why I'm talking about this equation. But what's interesting is that we can notice two facts that seem pointless to express in one dimension, but in 2 and 3 dimensions become important facts and indeed unlock the key for how to actually solve these problems. So one is that v of x is the average of its neighbors. Okay, so why is that so? Well, let's actually draw a little graph here of what v of x might look like. So that might be v of x, just a line because it doesn't have acceleration. So we can express this as v is equal to 1/2 v of x plus r plus v of x minus r. Okay, so we just basically take a point and go the same distance either way and take the average, and that's going to be the potential at that point. The other thing that's interesting is that there's no local max or min. And looking at a straight line, that should be obvious. The max or min has to occur at the endpoints, unless you have it flat with no slope at all, in which case, every place is a max and a min. When you're finding maximum and minimum, we're going to look for something where the second derivative is 0. No, the first derivative is 0. I'm sorry. And the second derivative can be positive or negative, right? So the first derivative is 0. So the slope is 0, and what that represents is, either you have a case where, it's cresting at the top, or you have a case where it's like a valley, right? In that case, the slope is 0, but the acceleration is going to be positive or negative at those points. And if you have a negative acceleration, that means you're at a maximum, and a positive one means you're at the minimum. The other interesting thing that's not, well, kind of falls out of the two of the above, but actually the potential, when you give it the boundary conditions here, finds the minimum line length that'll get you from A to B. So, and that's kind of an interesting thing to know. Okay, next we do 2 dimensions. Fun.